stop sharing. And I will remind all of you that you just heard this meeting is currently now being recorded. So please be aware of that. And the first speaker is going to be Aarynn Carter, who will be talking about directly imaged exoplanets with Webb.
Okay, thanks very much to the organizers for giving me a chance to talk today. For those who don't know me, Hannah just mentioned, I'm Aarynn Carter. I'm a final year PhD student at Exeter. And then fingers crossed, hopefully at some point, I'll be able to relocate to the US, where I'm going to hopefully carry on doing a postdoc at Santa Cruz. So today I wanted to branch out maybe a little bit and talk about direct imaging of exoplanets with JWST. So to do so, the first thing I want to do is maybe prompt the question of why JWST? Why should we perform direct imaging observations at all over the stuff we have from the ground? And to be honest, whether it's direct imaging or anything with James Webb, I always like to think about it in terms of three key qualities: this sensitivity, wavelength coverage, and versatility. So James Webb is the largest telescope we've sent to space so far. It has this huge 6.5 meter primary mirror, and just as an inherent result of that, we can probe fainter and fainter objects, which is really useful for direct imaging because, as I've shown them some GIFs here on the left, we're trying to image these tiny specks of light basically right next to a really, really bright star. So the fainter we can go and the more sensitive we can be, the better our observations are going to be. And furthermore, from the ground, we constantly have to fight with this atmospheric distortion, which sort of throws the stellar light all over the detector and makes it almost impossible to figure out what's star, what's planet, or whether it was even a planet there to begin with. And we can correct for this a little bit with adaptive optics, which can do a reasonably good job, but being able to go to space and just cut that out completely is just really, really useful. Secondly, we have wavelength coverage. So James Webb has this huge wavelength range from 0.6 to 28 microns. And this is really useful for imaging exoplanets because it's at these wavelengths that the exoplanets become brighter, and not only do they become brighter, but their stars become dimmer. So what I'm plotting here is not the SED of a planet, but its relative flux versus solar type star. And from the ground, where we're typically limited to below 2 microns and maybe 4 microns with some photometry, we're really limited, I would say, to sort of around 10 to the -6. So these kind of hot objects, which for a given age is something more massive, and is why direct imaging has this sort of, I wouldn't say stigma, but this personality to it that it only observes these heavy mass objects. But as we move to the mid-infrared, where we can't observe from the ground, these cooler objects become more and more luminous, and the flux relative to their host star reduces. So the hope is with James Webb, particularly at 4 to 5 microns and beyond 10 microns, we'll be able to pick out these lower mass objects. And finally, we have this versatility. So I'm sure many of you know, but James Webb has these 4 instruments: NIRCam, MIRI, NIRSpec, and NIRIS. And across them, they host this huge range of instrumental modes, spectroscopic imaging, and even for direct imaging, in some cases, we can do these spectroscopic observations. So being able to do this when we want to, and do imaging and specifically coronography when it's necessary, when we really want to push the sensitivity, is really useful. And I'll just come back here for one more second, just to reiterate, really, I think it's important when you consider these observations, not just to think about James Webb as this really sensitive telescope, but the fact that it's sensitive over this new unexplored wavelength range, and it provides this really diverse versatility in all these different instrumental capabilities over this wavelength range, which really let us tailor our observations to our science needs. So I went back, I think the slides messed up there. Okay, so I do want to briefly talk about this. I don't have too much time, so I can't touch on it completely, but I do want to talk about the early release science program, the direct imaging one. And I'm literally just going to give you this one slide and talk about our targets for a second. And what we're planning to do is, I would say we can cluster this into 2 groups. So these observations of these high mass, the exoplanets / brown dwarf kind of objects, HIP 65426b and VHS 1256b. And in the former case, we're performing coronagraphic photometry to try and characterize its atmosphere, whereas for VHS, because it's so far separated from its host star at 8 seconds, we can perform direct spectroscopy. So in both cases, the idea is we're trying to characterize the atmosphere, particularly at wavelengths where carbon species might be producing absorption features. We can constrain the C/O ratio, perhaps get indications of their formation history or migration history, disequilibrium chemistry, or even clouds at the longest wavelengths, cloud abundance and composition. And then we have a disk target as well, HD 141569A. And again, because these rings are a bit close to the host star, we need to use coronagraphy. But the idea here is that these observations can constrain the disk properties and probe the emission of the disk directly. But also as a sort of handy side effect, you may have noticed there's these clear rings in the system. And the suggestion is that maybe there's some planet carving these gaps in the ring, and perhaps doing these observations, we can detect the planet or at least provide constraints on what isn't there. And I leave the link here for more information if you would like to read. I think there's a full talk connected on that website somewhere. So what I want to spend the bulk of my time talking about is recent work I've been doing in sort of estimating the overall mass sensitivity limit of James Webb direct imaging. And I think a good way to frame this discussion is to bring up this plot, which I'm sure many of you have already seen, but is the planet population in terms of, or the known planet population in terms of mass and semi-major axis. What I want to draw your attention to is the population here of imaged planets. So as you may notice, they all occupy these high masses above 2 Jupiter masses, and mostly at wide separations as well. And this is just a limitation of the observations. Smaller exoplanets are less bright and therefore more difficult to observe next to a giant bright star. And similarly, planets that are closer to their star are closer to that giant bright object and really difficult to pick out. So I frame it in this way because I think a natural question that comes from this is, okay, well, if we did a James Webb imaging survey, what sort of region of parameter space might we expect to explore? So I decided to follow this question a bit. And the first thing I think you need to answer is, well, what sort of targets should you observe if you want to optimally or select a broad sample of objects that can explore this parameter space? And in my case, I decided to focus on 94 objects in young moving groups. For those who aren't familiar, young moving groups are these sort of collections of stars that have common galactic motions. And because of that, we can sort of trace back where they formed from, and we can get quite a tight age constraint on these moving groups. This is really valuable for direct imaging because all we can do really is grab an estimate of the flux from our planet when we see it in an image, and being able to convert that magnitude using an age and an evolutionary model of what we might expect the mass of an object to be at that age for a certain magnitude is just really useful. But as I show in this plot here, this is a collection of different moving groups. And in general, they're all over the place. So I wanted to focus on 2 in particular, TWA and BPMG, with the reason being, well, firstly, they're nearby. So the angular scales we probe in an observation correspond to, the angular scales we probe in an observation correspond to smaller and smaller physical separations. So we're pushing to the left side of that plot, which is really what we want because that's where we expect more planets to actually exist. And similarly, additionally, they occupy this really nice region of age parameter space where their ages are old enough that planet formation is largely ended and the planets are there, but young enough that they haven't sufficiently cooled. So they're quite self-luminous and we can still detect them easily. So then we've got these targets. What mode should we observe them in? And I won't go into each individual one, but in general, we wanted to pick, I went for the coronagraphic modes because it's with these modes that we really reach the smallest separations where we expect more planets to be. And then finally, the question, well, what filters should we use? And for coronagraphy with James Webb, actually, there's quite a diverse range of filters you can use, but for a survey kind of observation, I decided to, for the NIRCam in particular, to focus on these broad wavelength F356W and F44W filters. This 444 is really great because it spans that like 4 to 5 micron peak I pointed out earlier. Whereas the F356 I more include as a comparison because it lies directly on this huge, like particularly methane absorption feature. So having that as a comparison I thought would be a nice idea. And then for the MIRI simulations I wanted to perform, you might think, well, naturally we should use the most longest wavelength filter, but in reality, the coronagraph that you have to pair with this filter to use it is enormous, and basically covers up the entire inner region of your detector. So I couldn't pick that one, so I picked the longer, the next best, which is this 1550. And then of the other two, I picked the 1140 over the 1065 because it's on the 1065 is directly on this ammonia absorption feature, so there's less flux there. So with that, those questions sort of answered, and this sample and this idea of a survey put together, you can go about estimating what the coronagraphic sensitivity for such a survey might be. And the way I did this, the first thing I did is I simulated full observation images with this package called Pancake, which is made by Space Telescope. And all that does is it's an accurate simulator, or well, as accurate as we can expect it to be, a simulator of the coronagraphic capabilities of JWST. So the idea here is for every object in my sample, all 94 of those objects, I simulate a target image, and you can see this residual scattered starlight that is left over in the image. I won't go into too much detail, but I perform this sort of reference subtraction process to get rid of that stellar light through a means we might expect normally. And then we end up with this subtracted image in the end. And there's no planets in this image. I didn't inject anything, but what this subtracted image does give us an idea of is this overall sort of underlying noise of our observations. What's the best case or the realistic case noise we could expect? And with that in mind, I will say, like, there's a huge amount of assumptions and decisions that go into this, but in most cases, I'm picking a realistic scenario. It's not pessimistic, it's not optimistic. If you are really interested, I can talk to you about all of these, but yeah, if you want it in your mind, it's more of a realistic guess. So using this image, we can produce the detection sensitivity. So what we do here is, as a function of separation in this subtracted image, we can grab an annulus and determine the noise in that annulus. And then we can go, okay, well, how bright would an exoplanet have to be to overcome that noise and be detectable to us? And that's what I sort of show here for one of the targets in the sample with these curves here, each one for its own individual filter. And now this is a useful measure because if we know the detectable magnitude and we know the age of the system because we picked these young moving groups, then we can say, okay, with an evolutionary model, what mass would we expect that magnitude to correspond to? And then we can convert all our magnitude sensitivities to mass sensitivity. And immediately already you're seeing that these curves are reaching sub-Jupiter mass sort of sensitivities, which is pretty much never been done before for direct imaging. So with that, we can say, okay, we're still in separation in arc seconds. Let's convert that to semi-major axis, this actual physical separation, because you can't just do a straight conversion, because a planet at, let's say, 100 AU will occupy a range of different angular separations depending on its orbital characteristics such as eccentricity or the inclination of the system itself. So what I did is I got the help of Mariangela Bonavita, and she used her QuickMass code to produce these what we call completeness maps or detection probability maps. And the main takeaway here is these contours represent the fractional probability that a object of that mass and at that separation would be detectable in our image, given the mass sensitivity curve that we just calculated. So using these, we can now, instead of for a single object, average them all together to get an idea of, well, what sort of parameters to base do we explore over a broad population of a survey of objects. So I've done that, and I broke it down here in terms of the 64 Beta Pictoris objects and the 30 TWA objects. And in general, you can see, irrespective of moving group, towards the longest wavelengths, with MIRI, you're observing the lowest mass, sub-Jupiter mass exoplanetary companions. And between the two, you can also draw some comparisons in that the Beta Victorious members are generally superior at the smaller separations. And this is because they tend to be closer to us than TWA members. So the same angular separation corresponds to a smaller physical separation. And then the TWA members are generally more sensitive to the smallest mass objects. And this is because they are younger than BPMG, so that the planets are still a bit more luminous, a bit easier to detect. And then I also broke it down in terms of spectral type, and you can see, irrespective of spectral type, the same trend. So towards the mid-infrared wavelengths, that's our best bet at observing these lowest mass exoplanets. And in general, actually, M stars are the best targets for imaging the lowest mass companions with James Webb. So this is a little bit of a contrast to ground-based, as I mentioned here, because from the ground, we have to do these adaptive optics corrections. And typically that relies on quite a bright star, or at least a bright reference star, if you don't have a bright star, to figure out what those wavefront errors are and deform the mirror correctly. So to finalize, I just want to show this one plot. So what I've done is I've taken the full sample here, the 64 BPMG and the 30 TWA in the 1550 filter. And this is the average completeness map. And you can see that we're definitely going to be able to push into a region of parameter space that many direct imaging planets have just not been discovered in. And I think it's good to split this into sort of two regimes. I think one is maybe beyond 100 AU, where we're definitely going to get down to 0.1 Jupiter masses. But I would be tentative to think that there might be a lot of stuff there, because I think current understanding is that there might not be many things there to begin with. So what might be more interesting actually is this region here between 10 and 100 AU, let's say, where when we're not quite pushing down all the way to 0.1 Jupiter masses across the full range, but we're definitely probing at some separations down to sort of Jupiter mass and Saturn mass objects over a broad sample of targets. So I think this is really interesting, because I think thus far we've sort of thought of transits and directly imaged planets as quite dichotomous. They're two different populations, and perhaps with James Webb, if the sensitivity is good as this predicts, we can start to sort of blend these populations together and perform more robust comparisons between the two. So I think I'm a bit short on time, so I'll just leave my conclusions up and say thank you very much, and I'll take any questions.
All right, thank you. Yeah. People have worked out the clap emoji. Excellent. Do we have any questions? Please use the raise your hand feature or type them in the chat.
I'm trying to find the chat.
If not, I'll start if that's okay.
Okay.
I was wondering, so you were showing that the MIRI filters are probably the best and the M stars are probably the best, but how much do you want multiple filters for each of these planets? And therefore, is there a phase space where multiple filters work best for a type of star or distance?
Yeah, I would say, so multiple filters, I think you definitely want to detect the object in more than one filter, particularly because you might not know whether it's some background star or something like this. So the F356 is a good comparison to the F44W, because a star, for example, you would expect to be bright in the F356, but you wouldn't expect a planet to be bright in that. So that's one reason why you might want multiple filters. But in terms of purely a detection survey, I think you might want to just focus on a small number of filters and then do follow-up characterization, if that's sort of what you're getting at with your question.
Jessica Crick has a question, if you want to unmute and ask that. Give them a moment. Don't have a microphone attached. So I'll ask the question. This is from Jessica. What sort of observing times are required to do this for the suggested program that you've designed here?
Sorry, can you repeat that?
What sort of observing times are required to do the suggested program?
Yeah. Okay, so the observations I've done here are not very sensible scheduling wise. I've done a independent reference star for every single object. And because of that, things kind of get slowed down. You might be able to use the same reference star for a range of objects, or if you had like a library of reference observations already, you might be able to do those subtractions. So I will say, like, right now, if you did the survey as is, it would take like over 500 hours, which is pretty outrageous. But I would say a huge proportion of that, I would say like 90% of that, is the reference star observations. So if you can cut that down, you could totally make a more reasonable, tighter survey. And as well, you don't have to do all 94 objects, right? You could pick some subset of that. And in fact, actually, I will point out the GTO, one of the GTO programs is doing a M-star survey of 10 M-stars, I think. I forget exactly how long that's going to take, but it's definitely feasible to do this kind of stuff.
Natalie Patalia has a question.
Hi, Aarynn. Thanks for the talk. I love your graphics.
Hey.
Very, very well done. Maybe I missed your point. I was taking notes and I missed, I think, a key sentence. But back in your detection probability curve where you've got the observed planets, yeah, that one.
Yeah.
There's an interesting, the 0.8 or the 80% contour. So that's really high detectability. And down near the trough, there are very few planets. I don't know what the two diamonds are that are gray, maybe like, well, I don't know, ellipsoidal.
Yeah, I'm not entirely sure what they are. My guess would be some sort of timing observation. But
pulsar timing maybe is way out there. I don't, well, no, that doesn't make sense either. I don't remember. But I thought that you said that you expect few planets down at that trough of that tongue. What, or did I misunderstand?
Well, I mean, I'm definitely talking from sort of what I'm remembering right now, not hard, solid facts, but from my memory, I think from population, I think like the Forgan et al., like 2013, when we do this planetary population synthesis stuff, we don't really expect that many objects at these separations, particularly beyond like 500 AU. I think there's really not much they simulate out there. But maybe more towards here, like you say, I think maybe that goes up a little bit. But to be honest, to give you a robust answer on that, I think I'd need to go and look at the simulations.
Okay. Yeah, I think that that's a very interesting part of parameter space. The detection contours for both transits and RVs are a diagonal that goes from the bottom left to the upper right. So we really haven't had any sensitivity down there to say anything meaningful. And maybe that's a sweet spot for Webb to break open.
Yeah.
Thanks.
Bjorn has a question.
Yeah, so very nice talk. And I have one question. So the curves that you showed, I guess you must have made some assumption for how much total exposure time you assign to a certain target. Can you comment a bit on how this scales with exposure time? Because from the ground, there's often kind of a plateau. At some point, even if you spend more time, you're not going to gain very much anymore. Is that the same with James Webb, or will a lot of exposure time on a certain target actually give you deeper and deeper sensitivity?
Yeah, so the exposure times for these are like an hour. So every target is an hour of an observation. And I think there's sort of two different regimes where if you start to observe more, it doesn't really help. And if you start to observe more, it does help. So particularly at the closest regions, you're not sensitivity dominated, you're contrast dominated. So the issue is not that this background sensitivity that you're trying to reduce, it's the fact that there's a giant bright star there. So at some level, no matter how much you observe, that's going to be the dominant factor, particularly I would say in this sort of curving region. Where it sort of plateaus, I can't give you any like strict, I haven't tested this, but I don't think it would improve drastically past an hour at these very wide separations as a sort of qualitative statement.
Okay, thank you.
I'm going to wrap it up there. There are a couple more questions in the chat, Aarynn, if you want to have a look there. And then Aarynn and Munazza, who will be talking next, will be hanging out after all of this. So you can keep asking questions, then we'll moderate the chat again. So Thanks. Thank you. Can we thank Aarynn again, please? Munazza, would you like to share your screen?
Yes.
Munazza is going to be talking to us about transmission spectroscopy of WSP 62b.
Alrighty. So for those of you who don't know me, my name is Munazza Alam, and I'm a graduate student at Harvard. And today I'll be talking about the optical transmission spectrum of the hot Jupiter WSP-62b and why I think it's an exciting JWST community target. So some of us here may recall that WSP-62b was selected as a potential transmission target by the JWST Early Release Science Program, contingent on the cloud-free nature of its atmosphere. This is a figure from the 2016 ERS paper led by Kevin Stevenson, showing the JWST visibility windows for a handful of bright targets. And we see that WSP-62b is particularly advantageous because it lies in the JWST continuous viewing zone. And with the launch of TESS, we've actually found 5 giant planet candidates that are near the south ecliptic pole, but none of these candidates have as yet been confirmed as planets. Some of these TOIs actually show evidence of blending or V-shaped light curves, which makes WSP-62b particularly special because that means it is currently the only known transiting giant planet in the JWST CVZ. It's also got a predicted scale height of about 180 parts per million per scale height for a cloud-free atmosphere, but we had no evidence as to whether or not WSP-62b had a cloudy or cloud-free atmosphere until now. So we observed 3 transits of WSP-62b as part of the PANSET program, which is led by David Singh and Mercedes Lopez Morales. PANSET stands for the Panchromatic Comparative Exoplanetology Treasury Program, which was awarded 500 orbits on HST to observe the atmospheres of 20 giant planets in the UV, optical, and infrared, with the goal of assembling the first statistically significant legacy sample of exoplanet transmission spectra that are well suited for follow-up with JWST. So we observed 3 transits of WSP-62b with the STIS instrument mounted on Hubble, which provides spectroscopy between 0.3 and 1 microns. These are the raw and detrended white light curves for each of the visits, and I'll note that there were some guide star issues for both of the G430L visits that resulted in a lack of data in the first orbit for the first G430L visit and very few exposures in the second visit of G430L. But the data that we were able to extract are good quality and we're able to get a good spectrum out of them. So we binned the G430L and the G750L observations into 29 wavelength bins, and we also combine our STIS observations with existing Spitzer photometry. These are the detrended Spitzer light curves overlaid with the best fit model for the 3.6 micron channel on the left in orange and for the 4.5 micron channel on the right in pink. And so putting this all together, we find that the optical transmission spectrum of WSP-62b indicates evidence of a cloud-free atmosphere. So here the black circles are the observed spectrum, and we ran a retrieval analysis using the Poseidon code written by Ryan McDonald, and the best fitting retrieved spectrum here is shown in the blue line, and the purple shaded regions are the 1 and 2 sigma confidence intervals. The best fitting model from our retrievals is consistent with a cloud-free atmosphere with no stellar contamination. We did run our retrievals with a stellar activity prescription because we have some X-ray and UV photometric monitoring of the star that suggests possible flares, and so we wanted to make sure we were properly disentangling the stellar and planetary signals here. So the spectrum is characterized by a signal of sodium absorption at 5893 angstroms, which we detected about 7 sigma confidence. And we also see the pressure broadened wings of the sodium line, which is driving the cloud-free solution for the retrievals. Interestingly, the retrievals also pick up this little bump at around 0.4 microns, which could tentatively be evidence of silicon hydride, or SiH, which I'll talk more about later. We also see some pretty large scatter in the red part of the spectrum, and the retrievals show some non-significant detections of water, ammonia, and iron hydrate, which may be driving these last few, which may be driven by these last few data points. And so, actually to test this, we ran retrievals excluding these last few bins, and we found that the 3 reddest points are driving the FEH inference, but all the other results remain consistent, which suggests that the peaks of water and ammonia are not being driven by these particular data points. I will also note that while the STIS observations suggest that WSP-62b is cloud-free, observing the presence or the absence of the distinct water absorption features in the near infrared, for example, with C3, prior to JWST is really important for confirming this finding, in addition to, for example, providing a strong constraint on the planet's atmospheric metallicity and its water abundance. Unfortunately, the existing WFC3 observations for this planet have been difficult to reliably extract information on this planet's atmosphere. Some of the WFC3 wizards, including a couple people here, have taken a look at this data set and found that the observations are not reliable for pulling out meaningful information about the planet's atmosphere. And to visualize the overall data quality of this visit, I've got a figure from a review paper by David Singh. And so here is a time series spectral pixel map for the WFC3 observations of WASP-62 that were taken with the G141 GRISM. And so plotted here, we have the normalized count level at each pixel in the spectra versus the time during the transit observation. And since there were some guide star issues during the transit, they actually impacted the telescope guiding, and we can see these large drifts on the order of several pixels here. And this actually impacts the photometric quality of the spectroscopic channels when we're constructing the transmission spectrum, and it also contributes to systematic trends which drift in wavelength during the observation. And for comparison, here's an example of a good quality WFC3 dataset which doesn't show these wavelength dependent trends. I will say that there was a recently published transmission spectrum using this data set, but for the reasons that I just outlined above, I think that particular observation is not good for reliably pulling out any information on the planet spectrum. And it's unfortunate that these existing near-infrared observations aren't reliable, because we know how valuable Hubble time is. And of course, they would also be really useful for confirming if this planet is cloud-free prior to JWST. But with the observations that we have in hand, I mentioned that there was a possible SIH feature that pops up in the retrievals at around 4 microns. And I was curious about this because we hadn't seen this before, and I was wondering if it was spurious. And especially because with the way that we construct the transmission spectrum, we take the weighted mean of the 2 G430L visits. And so I wanted to see if maybe this was being driven by one of the visits or the other. So we ran our retrievals for the G430L, including the G430L visits as part of the transmission spectrum separately. And so here's what the posteriors for SIH look like if we include the first G430L dataset only in the transmission spectrum on the left, versus if we include only the second G430L visit, versus if we include the weighted mean of the 2 visits on the right. And so what we see here is that the evidence of SIH seems to be coming from visit 58, which makes sense when we take the weighted mean because that's a more precise data set. But we also see that the lower probability tail for SIH actually becomes lower for the weighted mean compared to visit 58 alone, which suggests that perhaps the 2 visits aren't in strong tension with each other, because if they were, then the SIH uncertainty would have expanded with the weighted mean. And so it's possible that maybe the visit 57 data set is also consistent with SIH, but the larger uncertainties could be maybe causing the retrievals not to see it. But as for this tentative detection of SIH and the silicon abundance that we can derive from it, this is actually where I think the JWST related fun comes in. And in particular, we explore some predictions for infrared observations, since the SIH cross-sections show that there's some strong SIH features around 3 and 5 microns. But from equilibrium chemistry expectations for silicon-bearing species at the equilibrium temperature of WASP-62b, which is around 1400 Kelvin, it's possible for most of the silicon to reside in SiO or SiS, for example, rather than SIH. But this is a little bit difficult to discern at the moment because UV optical SiO cross-sections are not currently available, and we're also missing SIS cross-sections below 2 microns. But in any case, we did want to double check and make sure that we aren't mistaking one of these species for SIH. And so we took a look at some ATMO forward models for WASP-62b at solar metallicity, and we in particular looked at the abundances of water, SiO, SiS, and SiH for a range of C to O ratios from subsolar to supersolar. And so the vertical dashed line here denotes roughly solar C to Os. And so from this comparison of abundances, we noticed that even though SIH pops up in the retrievals, SIS, just looking at the abundances, which is shown here in red compared to SIH, which is shown in the light blue, it seems like SIS could possibly be a more likely silicon-bearing species. But as I mentioned before, it's harder to search for SIS in the optical because we lack currently available line list information. Interestingly enough, we also see that SIO, which is shown in the green here, becomes less abundant than SIS for even moderately supersolar C to O ratios. And we see that this follows a similar pattern for the water abundance, which also drops off at higher C to O ratios, just like SIO. And then to quantitatively assess how well we could possibly detect a silicon-bearing species with JWST, we performed some simulated retrieval exercises for different JWST instrument modes. And here's an example of our simulated retrievals for NIRSpec Prism mode. So in order to run these simulated retrievals, we generated a high-resolution transmission spectrum model that is consistent with the HST retrieval results. So the model included some sodium, some water, some ammonia, some FEH, and some SIH. And then we simulated JWST observations with Pandexo for one transit of WASP-62b with NIRSpec Prism, which provides spectroscopy from around 0.6 to 5 microns. And so here, we then ran our retrieval on the simulated data, and which is shown here in the gray points. And the blue line is the best fitting retrieved spectrum, and the purple shaded regions are the 1 and 2 sigma confidence intervals. And so from these simulated retrievals, we confidently detect all of the species that are included in the model, even for a single transit, with pretty good abundance precision, something like half a dex for sodium and something like 0.45 dex for SIH. And I think this is really exciting because it's a single transit with JWST, and the possible cloud-free nature of this planet, I think, could make it a really exciting community target for JWST. And so to summarize, from the STIS+Spitzer observations that we have in hand for WASP-62b, we have evidence for a cloud-free atmosphere, although we currently don't have the near-infrared observations to confirm this. But we performed some simulated retrieval exercises to assess the precision with which it would be possible to detect different species with JWST, with a particular consideration for silicon-bearing species. And I think this is interesting because silicates are important for cloud species, but it's hard to detect cloud compositions because we'll need MIRI to cover the resonance features around 10 microns. So perhaps these features could be a way to possibly measure gas-phase silicon abundances at shorter wavelengths. And then lastly, considering JWST launch delays both past and future, this target is even more exciting because it's located in the JWST CBZ, and it could be a potential benchmark cloud-free planet for atmospheric studies in the James Webb era.
Great, thank you very much. Can we all thank Munazza, please? Do we have anybody with questions? We have Everett with his hand raised. Could you unmute?
Excellent talk. I was wondering if you think we should keep trying with the Hubble Space Telescope, or we've failed many times on that, or you think we should, it's good enough with this potassium feature, we should just go for the, just wait and go with Hubble go with Webb without needing a Hubble infrared measurement?
You are asking a spicy question. I think so we've been trying with Hubble and it hasn't worked. I think trying again wouldn't hurt, especially because I'm very cautious to make a definitive claim for a planet being cloud-free in the near infrared just based on a sodium detection alone. And so I do think it is worth it to go ahead and try for WFC3 observations again.
Hannah, you have a question.
I do. Actually, sort of just a follow-up. how many HST observations, or I guess we're talking about WFC3 observations, would you need to do that? And then is there anything you could do observing from the ground, perhaps in that like Rayleigh tail, that could tell you anything?
So the unsuccessful Hubble proposals have been actually for one transit with the G141 GRISM, and we also tried in another iteration to also combine with G102 with C3 observations as well to kind of get coverage of the three water band heads in the near infrared. And so from our just simulations and kind of predicting how those results will come out, I think a single transit in either hope or both would be good for kind of confirming this. And from the ground, that's a good point. I think I will say that we do have some high resolution ground-based observations coming up for WST62 with Magellan, and so that might also be helpful for kind of putting this together and seeing what we can confirm with the data that we have in hand or coming in.
Cool.
Kevin, you had a question.
Yeah, so the NIRSpec Prism mode, it typically saturates around JMAG of 10 for the brightest pixels, but WST62 is brighter than that. So how did you handle did you look for saturation, and so how did you handle that in computing the uncertainties?
Yeah, so WST62 is around 9th magnitude in J-band, so it does saturate in the bluer part of the spectrum for Prism, but since the kind of aim was to look at and get some really good precision for silicon features out around like 3 and 5 microns, I was looking at other proposed observing strategies, for example, with TRAPPIST-1 to saturate in the blue part of the spectrum in order to build up signal in the region of interest in the spectrum. And so actually to kind of account for that in the simulated retrievals, one thing to do is so Pindex spits out which pixels are saturating and just kind of inflating the error bars accordingly and accounting for some saturation in that part of the spectrum. It's not perfect, but it's some workaround.
Cool, thanks.
Zach, you had a couple of questions.
Yeah, thanks, Munazza. I really like the consistency check between the retrievals for the two different blue visits. And I'm also just curious about the spectra themselves. Are they consistent with each other? And this is also kind of getting at a bigger question about asking you to speak a little bit more about the stellar variability and contamination issues that you looked into.
Yeah, so the spectra themselves, the two visits are fairly consistent with each other. It's just that the first visit has much larger error bars, and so it's kind of hard to put so much stock in that one visit over the other, and that's why ultimately we decided to go with the weighted mean of the two spectra. And yeah, I was very nervous about any effects from stellar activity in all of this, because spurious bumps and wiggles in transmission spectra should be taken cautiously. And so we do have some X-ray observations and some UV photometry that indicate evidence of two flares. Actually, what's really cool, and it's unfortunate that the C3 observations don't work out, the X-ray observations were actually taken on the same day as the WFC3 transit. So if it was usable, it actually would have been a really cool test of activity levels and things. So yeah, even more of a shame that it didn't work out, but that's life.
I was wondering, in the spectrum that you showed, there's a very low narrow point. Is that the search for potassium? Is it what's happening there?
I've seen this in a couple of different spectra. I don't know what's happening. I search for potassium, and that point is always super low.
Okay. If you change if you increase the bin size, does it then go back to kind of the continuum level you'd expect there, or
a little bit lower than the continuum level for a wider bin, but not exactly. Yeah.
All right, can we thank Munazza again? And I just remind you that both Aarynn and Munazza will be staying around for a bit to answer questions. So please stay on if you have any questions. But thank our speakers again, please. Also a reminder that in 2 weeks' time, we will have Ryan McDonald and, let me move this, Daniela, to talk about 2 more things related to our Exo-Webinar series. I'm trying to remember my questions. I had so many. Hang on.